So it'll be worse. Okay. All right. So let's go back. 1, 2, 3, 4, 5, 6. How many stereo centers? So we're going into the sugar stuff. How many stereo centers are there in this regular hexose molecule, which is just sugar? This is a 6-carbon chain sugar, so it's called a hexose. But how many stereo centers are there? Huh? Nope, not just one. No, there's not 2. There's not 6. And now everybody's just like guessing. Okay, that's right. There's 4. There's 4 stereo center. Is this one a stereo center? No, it's double bonded oxygen. So it's not a stereo center. Is this one a stereo center? No, because it's 2 hydrogens, so it is not a stereo center. This one is stereo center 2, 3, and 4. So if you remember from your organic chemistry or biochemistry and so on, you can actually have 16 different sugars. Hexose. You don't have to memorize the name, but the reason why you have 16 different kinds of sugar, because you have 4 different kind of stereoisomers. And essentially, if this one is simply flipped, you get 2 combinations. If this one is flipped, you get another multiplied by 2 combination. You get 4 multiplied by another 2, another 2. So essentially, you get 2 to the power of n. So we have 4 stereoisomers. 2 to the power of 4 is equal to 16. So we have 16 different kinds of sugars. You have, in this case, you have lactose, you have maltose, you have something else. All of these are pretty much the same in terms of their structure, except some of the OH is pointing upward or downward, and it's basically just a combination of things sticking up or down. And in which case, you give it a different name for that particular sugar. Now, the rest of biological systems essentially is just polarity as well as geometry, and we're just going to we've just finished talking about cis isomerisms, geometrical isomers, as well as chiral molecule, which is another different kind. And essentially, the biological system uses these kinds of things as recognition systems. So I'm not going to go into all the names, but what I like to highlight is that you can see between this one and that one, that's the only thing that's flipped. And if you go from here to there, there's one of them is flipped. So this is flipped between here to there. And essentially, if you flip the geometry, you get a different kinds of structure, and hence you get a different kind of sugar. And they have a different name. You do not have to memorize them. I just want you to recognize they are different. Since we are skipping into the chemical reaction, what I wanted to get to is that this is like an easier way to draw sugars, but in actuality, their shape in the body is actually more of this cyclic looking molecule. So they actually make what they call the chain reaction type thing, where essentially this double bonded oxygen is going to attach to the carbon where the oxygen here is located, and it makes an ether group that looks like a ring like that. But sometimes this is harder to draw, so hence we kind of settle with this, and with the assumption that one of the oxygen is going to attach to one of these places and create a different molecule altogether. Let's see what else. Right. And once you have, and if you think of the sugars as these hexagonal looking thing, the only difference between one sugar and the other is the positions of the OH groups. They can either point upward or downward, and the position of this one, of course. And essentially, you can think of them as like lock and key. And if you remember, one of the function of sugars, or essentially just is a recognition system, and they do look like a key. So sometimes you can also look at if you have cyclic molecule or cyclic alkane, sometimes it's drawn like sideways like this to emphasize their pointing up and down. And essentially, if you have a molecule that looks like this, it's going to be different, just exactly like the groove on your key, that they are different with a molecule that looks something like this, for example. And because they are geometrically different, they're going to be recognized in different fashion. And essentially, if you can also have different sugars in different part of the body, because if you want to control, for example, the chemical reactions of one part of your cell, you might want to use this kind of sugar instead of that one. So as long as you maintain a constant concentration of this one inside your blood cell, then you have more or less a constant reaction, and you don't have to make sure that the sugar is only concentrated here but not there. So even though it moves all over the place, as long as a particular part of the body recognizes only one thing to, say, allow them to burn the molecules and so on, then they're not going to recognize this one. So it's a bit more controllable, at least inside the body, or at least for a functionality like that. You can also use sugar. It really is just basically geometry. So if you look at your immune system and so on, the white blood cells recognize the different kinds of, say, cells, as well as bacterial infections and so on, by the kinds of sugars that's kind of sticking out on the surface of these lipid bilayers. And essentially, there really are just like grooves in your key. So one of them looks like this, the other one looks like that, and your immune system would essentially just attach to one that it recognizes as a bad thing, and then it's going to call Pac-Man to chop off the particular cell because it's recognizing it as a bad and invasive species or invasive type of material. So essentially, it's all about structures, and depending on how they're clumped together. In this case, you can use sugar as recognition system. You can also use sugar, for example, as energy storage. So if you have starch, there's a bunch of different starch, but I'm going to kind of clump them together. So if you have starch, where the sugar molecules, so each of these hexagons are sugars, have multiple branches that's sticking out, they can, in this case, at least for plant material, can be used as energy storage, or at least quick energy storage, because you have a bunch of ends, and if you have another enzyme that is able to kind of eat them, you can get, that's my Pac-Man again. So this is your energy storage, but because you do have a lot of ends here, you can chop them off on whatever end and start consuming energy fairly quickly in that regard. Right? So essentially, if this is a chemical reaction, you have a lot more surface area. So in this case, you can use starch as energy storage because the particular chemical structure of the starch molecules, the sugars are branched out and they kind of like a dendrite-looking structure. So energy can be generated from eating one side of the end to the other. Yes, there's non-reducing ends and so on, but I'm going to simplify it for now because I don't want to focus on those. What I do want you to notice is that they're structurally different, and they are, and it really is about biochemistry. They're all about structures. So if your sugar molecules, for example, instead of kind of being arranged in randomly branching molecules like starch or amylose, which is just kind of much shorter, instead they're kind of packed very, very tightly like this, then you get cellulose, which is what makes out wood, and wood is pretty much impenetrable, and it essentially now becomes the same molecule that can generate energy can now also become a protection layer because they are quite impenetrable. There's a bunch of hydrogen bonding here between one layer of sugar molecule to the next, to the next, to the next. They have a specific composition so that they pack as tightly as possible, and they become a pretty hard material. And they're also, unlike, say, the starch, they're also not very digestible. That's why we can't digest cellulose, because there's only, if you look at the actual structure of cellulose, there are kind of ends that are sticking out that can be consumed by enzymes and get unraveled. So, but majority of the time you have a huge surface of this thing, whereas there's only one end sticking out. So the process of trying to dissolve cellulose becomes a really, really onerous process and a very slow process. That's why if you have fungi growing on the surface of a dead wood, it takes a very long time to actually decompose the entire wooden fallen wood, because the enzymes of the particular mushroom, so let's say you have a big of a mushroom there, the enzymes are only able to break down the cellulose one layer at a time. So once this layer is done, they have to find another reactive end of the cellulose and just like take one layer off at a time. So it takes a very long process, because the cellulose are highly tightly bound together, so it becomes impenetrable. And of course, you can also have things like chitin. What is it? Chitin? Yeah, or keratin. No, mostly chitin. Insect shells, they do have some modification group on each of the sugar, but they're more or less sugar, and they're also the same structure. That is, they pack out nicely like this. So insect shells are quite hard because they pack nicely. So it's all about geometry, and what the function is going to be governed by the geometry as well. So the only difference between one sugar to the next, it's like the only difference between, whoops, where are we? One sugar with the next one, in terms of their function, they're still the same thing. There's just carbon, hydrogen, oxygen, the same number of carbon, the same number of oxygen, the same number of hydrogen, but they pack differently. And because they pack differently, they will generate overall a different structure. So chemically they're similar, but it's all about how they pack. And you'll find that that's going to be the case pretty much for organic molecules as well. Or as you continue with your biological system, you'll see these a lot more, and you probably have to learn about them in much greater detail. So why glucose is different in terms of reactivity versus, say, lactose versus mannose and whatever else. But we're not going to go into that because you don't need to know it for now. Those are specific that sometimes get lost if you focus on them too much. I'm going to skip this particular page. It's basically the same picture that I mentioned before. If you have a chiral molecule, your enzymes are highly specific in terms of geometry. So if you simply have a chiral molecule, one of the molecules flip with the other, then it may not be reactive whatsoever, or the reactivity is reduced by hundreds or more in terms of their magnitude. I suppose this one is the last one, chirality of the drug. I mentioned that before. In this particular case, the drug in this case is a chiral molecule. There's only one stereocenter, but one of them cures morning sickness, but the other one causes birth defects. So this particular kid doesn't have an arm. That's because if, but anyway, so and of course this is no longer in the market pretty much because, you know, not a good idea. They were available for a long time because people couldn't figure it out. It's like, it works. Yeah. Yeah. Do you remember her name?
I'm trying to look it up. My grandma told me
about it. I'll Google it out as well. That's kind of interesting. I should increase more of the historical perspective here. But the idea is the same. They're very similar. They're really just mirror images of one another, but one can cause one function, the other one causes a different one. They are All right, so that's the only conclusion that I want to say about the chirality, the geometry, the isomerism. They're really just about geometry. Oh, shoot. What happens with this picture here? Do you have that thing on your printout? No?
Yeah, it's different, but you have the effects on the.
No. Does it look like a WO on your thing? Okay. Is it?
It's a chart.
Okay, so the only thing that's kind of different is just that, right?
Yeah.
Okay.
Yeah.
Yeah, no, I think something wrong with the transition between one to the other. The next one that's very important is the intramolecular interaction, or I should say intramolecular. Intra for specific term between two different molecules instead of in between the same molecule. And essentially, for molecular chemistry, the major component is mostly just electrostatic interaction. That is, the more polar your molecule, the stronger its interaction is going to be. There's four general type because you have an ion, you have a dipole, you have dispersion, and you have hydrogen bond somewhere in between the ion and the dipole moment, right? So there's the type of interaction. We can go from like the strongest, which is ion-ion interaction, and we can go all the way to the bottom, which is a dispersion force or induced dipole. And I just want to kind of go that if you have an ion, say sodium chloride, the sodium is positively charged completely, and the chloride is also completely negatively charged. So this is the most polar, and it's going to have the strongest interaction. And the last one here, if you go all down to the bottom, I just want you to put, like, for the dispersion forces here, it's going to be the least polar. And it's going to be the weakest interaction. Huh?
I got her name, Frances Kelly.
Frances Kelly.
Yeah, she was on the FDA, the pharmacologist. She stopped the drug from being
Kelly with a K, right?
distributed. Yeah, or Frances Kelsey, sorry. She was also one of the people who got them to remove antifreeze from children's medications. It used to have a raspberry-like flavor. They added diethyl balsam, and she had them remove that. She was like a big part of like women in when they recognized women in science.
I should look that up. I have to tell you, I came from Indonesia, so I remember when I was like 8, I was playing with liquid mercury and started dissolving metals into mercury. If you put iron into mercury, it's going to dissolve it because liquid mercury is liquid metal, so like dissolve like, so metal dissolves metal. I remember that. It's like, oh, this is like an interesting looking thing. If you put a lot of metal, it becomes like really solid at the end. But so sometimes the safety things in Indonesia is not as strong here, so I should really look it up because it should probably be an interesting historical perspective. No, I don't remember where it was. Strong interaction, most polar. So if you look at sodium chloride, if you want to actually know how strong the interaction is, we should just vaporize it, because once you vaporize something, you literally break one molecule interaction with the other one, because now they're like meter apart from one another. So if you have sodium chloride, their boiling point, the temperature you needed to vaporize is about 1,700 Kelvin, so it's quite a lot. But if you simply mix an ion, so in this case sodium, with something that have a dipole like water, so the ion here is the chlorine is the ion, the sodium here is the ion, and the water here is our dipole. So water is a polar molecule, so it's an ion and dipole interaction. So if you have salty water, then the boiling point goes down, way down. to about 381 degree Kelvin. Again, it's not a linear scale, it's just kind of a relative level of interaction. So in this case, the interaction, the boiling point of salty water goes down to about 381 Kelvin. If you look at just water, which is the bonding is kind of a dipole. It's a hydrogen bond is a specific type of dipole-dipole interaction. The only reason that we give it a specific name as hydrogen bond is because it's almost ionic in some way. Hence, we give it a slight different name to it. But really, they're just dipole-dipole interaction. Water is more or less nonpolar, but you remember from your acid base that ion does dissociate. Hence, it's a bit ionic. So if you look at water, the boiling point is 100 degrees Celsius, so 373 Kelvin. You can keep moving down. So instead of a hydrogen bonding, so now we simply have a dipole-dipole interaction. So I have one methylene chloride molecule with another methylene chloride. O, C, H, H, H. So in this case, it's just a dipole. So this is my dipole moment, another dipole moment interaction. The methylene chloride is going to have less boiling point. And if you have something like methane here, the only thing that I'm changing from the particular molecule on the top is that I change the chlorine into a hydrogen. Then we have a methane. Then the boiling point of methane is 111 degree Kelvin, or it's about negative 160-ish degrees Celsius, which is why methane, or natural gas, is a gas at room temperature, because it's well above its boiling point. In which case, if you have methane molecule, which is nonpolar, interacting with another methane molecule, what we have is what they call a dispersion forces, and it's a very weak force. Now, even though it's called the dispersion force, they're all really just electrostatic interactions. Just you have some charge and positive and negative, and they just interact with one another. So what I meant by that is that the interaction is how they combine together. If you have sodium, which is Na plus, and Cl minus, it's pretty clear. You have positive charge and negative charge, and they interact, and they try to make this physical interaction through electrostatic forces. If you have, for example, sodium plus with, say, methylene chloride, you have the chlorine on the other end, which is highly electronegative, and you have carbon and hydrogen, hydrogen, hydrogen. So the majority of the electron density is going to be on the chlorine side, so this is going to be somewhat more negative, and it's going to interact with the sodium plus. So in this particular case, it's an ion, because sodium is an ion, and this is the dipole. So that's why it's called an ion-dipole interaction. You can also have, for example, an ion-induced dipole, which I haven't mentioned yet. I didn't actually specifically written there. So what I want you to remember is that dispersion force is the same thing as induced. Kind of, almost the same thing. Let's put semi-equivalent. So for example, I can have a methane molecule, which is more or less nonpolar, so 1, 2, 3, 4, 5, 6. And I can also have a sodium plus charge here. So what happens is that there's, in any atom, there's a bunch of electrons, and what happens is that if you put a really, really positively charged molecule on one end, this positive charged molecule is going to try to drain electron density towards itself. So what happens is that you have an induced dipole, that is, there's an electron cloud around this hexane. It's not very polarizable, but what happens is that you have a tiny bit of imbalance, and I'm trying to put like a really light negative charge, and there's a really light positive charge at the end. So hexane and positively charged molecules still have this interaction because they do have an induced dipole. So in this case, ion induced dipole. The hexane molecule here is non-polar, but just because there's a proximity of something that's highly polar, it polarized itself a tiny bit. So that's why it's called an induced dipole. this one, right. So if you have, which is a good point to clarify, if I were to have a positive charge with an actual dipole, which is this one here. Oh, I erased it, didn't I? I think I erased the other one. So if I were to have my previous example is ClCH3. Here, this methylene chloride, CH3Cl, already have a dipole moment on it. So this already have a dipole because CHHCl is polar. So the only difference is that hexane doesn't have an inherent dipole moment, or hexane is a nonpolar molecule, whereas methylene chloride or water, if you want to think about it, is already polar. Hence, it's not called an induced dipole because there's already a dipole in there. It's no longer induced because it's just a dipole. It's already there. The last one that I want to mention is, for clarity purposes, that all of this is just positive and negative, positive and negative. You have a slight negative charge on the chlorine, positive charge on the ion, so you get an interaction that way. Even with nonpolar molecules, so let's say we have 1, 2, 3, 4, 5, 6, 7, 8. So I have an octane molecule. So this is an octane molecule. If you look at an octane molecule, it's actually going to be a liquid at room temperature, even though this is nonpolar and this is nonpolar. But what happens is that electrons is going to slush around. It's an electron cloud, so they slush around, and on occasions this part here is going to be slightly more negative than others, and this part here, because the electron moved from one side to the other, becomes slightly more positive. So what happens is that it's going to induce the same effect or an opposite effect on the nearest neighbor molecule, that this becomes a bit more negative on one side and becomes more positive on the other side. But this is what it means by dispersion. It's still an electrostatic interaction. The reason why octane or your gasoline is a liquid at room temperature, or I should say used to be your gasoline, is because there's still a positive negative charge interaction between them. Not very strong because it's just a randomly slush around and suddenly it fits. Somehow, once in a while, they become opposite and they become attractive again. But in the overall, the net effect is going to be a positive or a net positive interaction. Hence, they don't liquefy as easily. Oh, sorry, they don't vaporize as easily. Just mostly just the more, but the more polar it is, the stronger the interaction. Now, what I do want to mention again is just as a little bit. You don't need to know this one just too much. Oops, it's hanging. Sorry. Hold on. Sorry. So if we were to kind of compare ionic interaction, so in this case, if we simply compare, my point is that the more polar it is, the higher the stronger interaction, intramolecular interaction. So if you have NaCl, it's a +1 and a -1 charge. So the boiling point is about 1700 Kelvin. But if we simply move from sodium chloride to magnesium oxide, which have a very similar crystal structure, magnesium is now a +2 and a -2, so it's much more polar. And you can see that the boiling point goes up to about 3900 Kelvin. So the effect is quite large. The more polar you are, the stronger its interaction. Later on, we're going to go into solubility as well, and that becomes a bit more makes sense. Now, the one here, the one that's my picture disappears. You should have it on your list because I see it over there. The next one is the effect of the size, specifically not necessarily just the carbon chain, but the effect of size in general. Is that if your size is bigger, means that you have more electrons. That's always the case, because if you go down the periodic table or you simply increase the number of molecules, you have more electrons. So if you have more electrons, you can have more dispersion. If you have more dispersion forces, that means the interaction goes up because you have more now, right? You have tiny interaction, but you have a lot of them. Like your not zipper, but like what do you call those things? Velcro. Thank you. Like each one of the Velcro interaction is very weak, but once you have a lot of them, if you have your Velcro, it's like a tiny hook. Individually, they're weak, but you have a bunch of them, they become a strong interaction. So, for example, if you simply have a methane molecule, which is CH4, can you tell me what the boiling point is again? Is that 100? Right. So CH4, which is just a methane, negative 161 degrees Celsius. Can you look for me for pentane? So now we have, instead of 1, we have 5. We have 36 degrees Celsius, so just above room temperature. Can you go to decane, please?
It's 174.
So decane is 174 degrees Celsius, and remember 174 degrees Celsius is even higher than the boiling point of water because decane is a much larger molecule than water, so you have a lot more of those dispersive or dispersion interaction. Hence, even though each effect is small, it's additive and they can be pretty big. If you simply look at your candle wax, which is somewhere around 18 to 22, candle wax is not that exact. The boiling point of this one is around 300 degrees Celsius, around 275 to 300 degrees Celsius. So you can see it's pretty high up there. The bigger the molecule, the more dispersive interactions it could add up to increase the boiling point by quite a lot. But if you want to remember anything, it's just the larger the size, the higher the dispersion interaction becomes. So 1, 2, 3, and of course if I have this, which I imagine is polyester, the polyester is really, really, really long. It's hundreds, if not millions, of esters interconnected together, hence polyesters, because they're really, really long. My jacket here will probably not melt. It will burn before it would actually melt because it is so long. The dispersive interaction is so high. It would just not melt. It may get softer and wobbles a bit, but it wouldn't really melt because the molecular size is too long. Which brings me to the more important portion, which is the big message is that polar molecules have larger interaction, and they have, in that regard, the boiling point and physical property is going to be different. These are some of the lists that I have on your list. You have methane, formaldehyde, and all I'm doing here is just formic acid. You have polar, very polar oxygen, so they're highly polar molecule, and the boiling point is 100 degrees Celsius, or almost equivalent to water, just a bit more. If you have methanol, I'm replacing this double bonded oxygen with hydrogen. So methanol is less polar, so in this case the boiling point goes down. Formaldehyde goes down even more, and methane goes down even much, much more. So my point is that here, different functional groups have different polarity, which is going to be more important later. Specifically, I think I have, hopefully I put it on the list here. Okay, if you kind of go to the next page over, there's a different functionality and the degree of polarity. This is the one that you might want to just kind of have a feel for it. If you have phosphate, which is PO4 3-, it's naturally have a negative charge, so it's going to be highly polar. The amide, which is our amide, looks something like this. Nitrogen, double bonded oxygen, that looks like that. There's a hydrogen, then the amine, but remember the amine here have like a double bond. What happens is, sorry, I have a lone pair. Amides are highly polar because sometimes the oxygen is so electron withdrawing, it becomes like that. So you can have like a positive charge here and negative charge done. Positive charge here and negative side on that side. So sometimes amide could turn into a pseudo ion once in a while, hence it becomes more polar. What you want to remember is basically amide, carboxylic acid, and alcohols are more or less polar. And then you have like ketone, aldehyde, amine, ester, ether that are mostly nonpolar. And the last one here is as alkene and alkane, which is nonpolar. So in terms of their interactions, your amide and carboxylic acid and alcohol could have a dipole interaction as their predominantly strongest force. The ketone and aldehyde also have a dipole, but it's weaker. And the nonpolar one here is mostly dispersion. But what I want to remember is just mostly, they just have different degrees of polarities. And since we are going into biological system, their degree of polarity is going to make a lot of difference in terms of their structural properties as well and what they will do in water. Am I recording? Yes, I am. I think I've been going for like 2-3 weeks before where I keep forgetting to record or the sound doesn't record, which is kind of annoying. In any case, so these are some. I'm not going to go into specifically what is hydrogen bonding because it's one of those things that you can just Google. So maybe if we have time, we'll go to hydrogen bonding specifically and determine which one is hydrogen on, which one is not. But it's something that's easily Googled out. What I want to focus more is the solubility of a particular molecule and specifically functional groups. The rule for solubility that you want to remember is this one here, or like, dissolve like. Is it a different order than what I have? Oh yeah, it is. Like, dissolve, like. That's really the rule for solubility. Like, dissolve, like. So if you have polar molecule, it is going to dissolve in polar molecule. But if you have a polar molecule, it will not dissolve in nonpolar. And if you have nonpolar, will dissolve in nonpolar. Right, so that's a general set. That is like, dissolve like. And if it's opposite, then it doesn't dissolve in one another. Now, majority of the time, we're going to be interested in mostly in water. Anybody remember what the charge on water is, or more or less? Yeah. Okay. I thought I went over it, but that's fine. So oxygen here and water is H2O. Biological system is basically reaction in water, so we're just going to concern ourselves with water. And the best way to remember is that the oxygen is more or less about a partially negative 0.8 charge. So the oxygen is about negative 0.8, and each of the hydrogen is positive 0.4, so the bottom part here is positive 0.8. So that's kind of the partial charge in water, plus and minus negative 0.8. And remember, our rule is like, dissolve, like. Now, if you have sodium chloride, NaCl, the sodium is +1 and the chlorine is -1. So +1 minus 0.8, they're pretty similar. So sodium chloride is more or less dissolved, right? In water, you have table salt dissolved in very large quantity in water. Because their charges are very similar to one another. And in fact, if you look at your solubility rule, I'm trying to remember what you guys covered in 142, 14a, I don't think so. But if you look at the solubility rule table, you'll find that ions with plus and minus 1 charge are usually soluble in water. There are some exceptions, and of course, soluble have wide degree of solubility. Is it 10 grams per liter, or is it 10 grams per milliliter? There's some degrees of that as well. But usually ions with plus and minus 1 charge are soluble in water in large quantity because +1 and plus and minus 0.8 is pretty close. But if I were to go into ions with, say, ions with plus and minus 2 charge are not soluble in water. And the reason why it's not soluble is because if you go, your charge is +2 or plus and minus 2, they're too polar. They're much more charged than water. So what happens is that they really just like to agglomerate with one another than with water. So they not dissolve. They will not dissolve. And essentially, solubility, what it says like dissolve like, it's basically like a Goldilocks space. It's just needs to be just right, and then it will dissolve. Otherwise, it will not. So plus or minus 1 dissolve, plus minus 2 usually doesn't dissolve. There's some exceptions that you have to memorize if you're taking Gen Chem and again and so on. But those are exceptions than the norm. So for example, if I were to give out an example of SiO2, which is silicon dioxide or basically sand, sand doesn't dissolve in water because the silicon is a plus 4, and each of the oxygen individually are -2, so they're way too polar. So they will not dissolve in water because they're too polar. So there is such a thing as being too polar. In this case, plus or minus 2, at least in water, is way too polar. You can dissolve sand in a solution of zinc chloride if you melt it, but that's a different story altogether. Now, what's more important is that for the functional groups, you can start seeing things that will dissolve and not dissolve in water. So these are examples of polar molecules. You have water, your sodium chloride, and so on. So these molecules will dissolve in water. So are the functional groups that are highly polar. So if you have alcohol, so ethanol, which is that one, will dissolve in water in actually 100% quantity because they're highly polar. Methanol, which is basically moonshine, will also dissolve in water. So ethanol will dissolve in water 100%. Methanol will dissolve, you don't have to write it down, but I wanted to get a picture of it. So methanol will dissolve completely in water. Propanol, which is that one, will dissolve in water. But once you get to butanol, it's only going to be sparingly soluble. You can get about 5% soluble in water. And once you get to pentanol, this will not dissolve in water at all. And mostly because even though this OH group, or the alcohol, is polar, you're increasing the level of its non-polarity because you have larger and larger of these alkane chains. And if you look at from the list of non-polar group, alkanes are highly non-polar, so they will not dissolve in water. So, something along the line. And of course, you can also have the same thing. So you can have acetic acid, which is a much more polar group than water. This will dissolve in water. But once you have like fatty acids where the alkene chains is really long, then the solubility goes down. And of course, if you have water and you try to put in carbon tetrachloride like this, which is entirely nonpolar, or say, I don't even know what that is, some kind of pentane molecule, this is nonpolar, they will not dissolve in water. So is your naphthalene or benzene. So naphthalene is your mothballs. If you have mothball, if you try to dissolve it in water, it will not dissolve because the structure looks like this. Aromatic groups are nonpolar. They will not dissolve in water. Oh, I do have the list over here. So yeah. What else? So we've covered functional groups, polarity, what will and will not dissolve. So essentially polar will dissolve, non-polar will not dissolve. Let's see. If I have, so suppose that I have two different kinds of solvent. I have water and I have hexane. Will this particular molecule dissolve in water, or will this particular molecule dissolve in water or not? No, it's a cyclohexane, so it will not dissolve. But because this is nonpolar, it will dissolve in hexane, which is also nonpolar. If I were to have, say, methanol, it will dissolve in water, but it will not dissolve in hexane. If I were to have something that looks like this, this will dissolve in water, but will not dissolve in hexane, and so on, mostly because the the degree of polarity is much different. So those are some of the effects. I'm bringing out hexane here just because if you're looking at the more common examples are, say, paint. If you're a paint scientist, most of the time you're dissolving things in hexanes, pentanes, or pentanol, and so on. So if you have an oil paint versus acrylic paint, you shouldn't mix them together because one of them is oil-based, which is mostly nonpolar. There are other things that are kind of interesting for biological system. If you look at your fatty acids, they more or less look something like this. And if you already flip through the structure, or flip to your thing, you'll see what the structure that would make in the end. So fatty acid more or less looks something like this. I'm not counting exactly how many carbon chains that I have here, but these are alkanes, and they're highly nonpolar. And this one here is carboxylic acid group, which is highly polar. So what happens if we were to try to dissolve a large quantity of these kinds of fatty acids in water? Right. So if I were to try to dissolve this thing in water, which is polar, we have an interesting structure now because we have a highly polar group on one side and a highly nonpolar group on the other side. And essentially the structure that one will make is kind of reasonable. That is, the polar group is going to try to interact with the water, which is also highly polar. But the nonpolar one is going to hide away from water because it doesn't want to interact with it, or water doesn't like it very much. So what we get is a structure that looks kind of like this. So water is polar, so the polar head is going to try to, as much as possible, interact with the water. And the nonpolar one is not going to dissolve in water, so it's going to clump up together. So essentially what you're going to make is this new structure, which is generally called a micelle. Micelles. I think it's double L or single L. I don't remember what the spellings are. So now you get things like this. And if you look at your fat molecules, they're kind of globular because the nonpolar chains are clumped up together. So you get clumping. If one were to use soap, the molecular structure of soap looks very similar to this, although sometimes they change the carboxylic acid to quaternary ammonium, which is even more polar, and you get the same particular structure. And the reason that soap can dissolve oil, cooking oil and so on, is because the cooking oil are highly nonpolar. So if you have oil, which is nonpolar, as you lather the soap on your hand, you're essentially trying to make as much as possible these micelle structure by violently rearranging its molecular structure, and you're going to start to trap the oil in between this nonpolar region because the oils are nonpolar. So now the whole structure, more or less, it's still somewhat soluble in water, and as you rinse out your solution, or as you rinse your water, you're going to continue to trap oil inside these micelle structures. And they're basically going to continue to flow out. So you have a bunch of micelles, and each of these micelles carries with it a large quantity of oil inside of its structure. Again, it's all about structures and what they will make. And as you rinse your hands and flow the water, it comes out to the sink in this particular globular fashion, so making a micelles. So I mentioned today as well a lipid bilayers, and lipid bilayers and the molecular structures of it look something like this. So you have a squarish looking thing, a rigid square, as well as a long carbon chains of molecule. So usually 3, so that's triglycerides, tri for 3. And the structure that it will make inside water is going to be a bilayer or lipid bilayer because these squares are polar and rigid. So they can't kind of circle around it. You're putting cubes together, so they're going to make kind of a line instead of a sphere. And essentially the structure they would make is like a layer like this. Now these particular structure, all that arises from it is just polar and nonpolar interaction. And what happens that if you have a structure that looks like this, I am going to try to replicate the picture that I have in my drawing there. Where is it? If you continue with this, you get essentially a cell wall that is impervious to water, because you have a layer of wax, really, in between your polar skin. So water, it's not penetrable by water. Hence it becomes a compartmentalized portion of your cell. So if you have compartments on your cell, they're always made of lipid bilayers because they're water resistant. They're a layer of wax, so the water can't get through. And of course, if one were to try to control the biological system one way or the other, you put a bunch of proteins in it, and the protein molecules, say, if you look at the properties of ion channels, you'll see that the head of the ion channels are highly polar, and then you have especially proteins that are stuck on the membrane side of things, and you have the membrane side of the proteins is going to be highly nonpolar. That's why it kind of lodged itself right in between the lipid bilayers, and that's kind of when it allows calcium channels to go in and out and so on. But the reason why that particular protein lies in between is because when it folds and so on, there's a large non-polar looking tube here in the middle, and it just kind of, it likes to be in non-polar region, so it sits right there and pretty much happy with it. So that's that in terms of the importance of polarity. Another important part of polarity is that if you have proteins, for example, I mentioned proteins now, so I should just mention how proteins fold as well. So if you have amino acids, long chains of amino acids, so you have amino acids, let's say this is polar, this is polar, this is polar, the amino acid then will fold, and let's just say we have a long chain of it, and after this particular thing, you have nonpolar, another nonpolar group in your amino acid, nonpolar. So what happens is that if you kind of shake the protein and they try to fold themselves, what happens is that the polar one will be on the outside. So if this is the shape of your protein, the polar proteins are going to be outside and they're going to face the water, whereas the nonpolar one is going to be the one on the inner region. Nonpolar. And they're basically going to be in the inside of your protein because they don't like water, or I should say water doesn't like the nonpolar molecule, so it's going to try to push it away from itself, and it folds in a particular fashion based on the level of polarity, which is why the same thing. So if you have molecules and proteins and enzyme, if you load it up with lots and lots of salt, sometimes it stops functioning because you have a sudden change of polarity in terms of the liquid, so it's going to try to rearrange itself, especially if it's a shock, and then your proteins stop functioning. So hopefully at some point, if you ever take biochemistry and kind of protein purifications, laboratory and so on, you'll see those experiments and you'll realize that you have to add the salt slowly to your protein so it doesn't disassemble itself. Disassociate. No, that's not the proper term. But anyway. Any questions so far in terms of the intramolecular forces as well as the structure that it makes, which is right here, some of the important structures in biochemistry. Pretty much what I asked you now. So if I were to dissolve the fatty acid here in hexane, what the structure would look like. So if I dissolve this thing in water, then it will make that. So if I were to dissolve this in hexane, what would happen? Huh? It would? No. It is soluble, but what kind of structure it would make if I were to dissolve this in hexane instead of water? Yeah, same thing. Right? Same concept, except now I'm just switching out the solvents. So That's basically it's going to be called, if I were to dissolve this in hexane, the structure that one would make is that the polar head is going to be the inside because the solvent is nonpolar. So this is called an inverse micelles, and you don't have to write that one either. You just need to know what the structure would look like just based on polar and nonpolar. So this is an inverse micelles if you're making nanoparticle synthesis and so on. You want to make sure that the metals are stable in the solvent that you're using, so you basically cap it with a large group like this. Usually you're making inverse micelles. So something along that line. It's fairly reasonable, I think. Pretty similar. I'm just reversing one with the other. Let's see. We're at 1. This is going to be the major portion of your test, is what it's going to be. You have the polarity, interactions, and so on, solubility, and I do emphasize the solubility part because it's kind of a big portion, and everything else in biochemistry is just whether something is polar or non-polar, and it creates something else instead of another shape. Yeah.
Do you recommend any specific areas to study in part 1 and 2 that will be the cumulative part of the test?
You will see a bit on each one.
Okay.
I would say, yeah, a bit on each one.
Okay. But any specific areas that we narrow in on?
Not really, because it's pretty much the same thing, isn't it? The first part is just Hess's law. Really the only big chapter, as well as ideal gas law. And ideal gas law is PV equal to nRT, so you can either have to solve pressure, volume, moles, or temperature. It's the same equation. I haven't posted any. I would say the nomenclature practice is pretty decent.
You said this is a bigger portion, right?
No, sorry. This is going to be. There's not many things I can ask about polarity. I mean, that's as far as we go anyway.
You just say it's important.
Yeah, that's right. It's important to have keep in the back of your mind that everything else is basically polarity.
But if you ask something about the bond polarity, you're always supposed to know the
If I were to ask you whether amide is polar or non-polar, you should be able to know what it is or not, right?
Okay.
And yeah, something like that. So recognizing whether a particular functional group is polar or not is kind of important. Oh, would you be able to? If I were to have a molecule, this is a harder one. It will dissolve in water and hexane. Then the boiling point is going to be less than 100 degrees Celsius. The melting point is going to be around 20 degrees Celsius. And I can make things more complicated, but I like this question, so you will not see it, I think. So if I were to give you these 3 parameters, which is the proper molecule? A, B, or C? Oh, this one is... Oops, where is that? Where it disappears. Where is it? Oh yeah, that's very smart. Thank you. So A, B, or C? Or actually, maybe we'll do it this way, so it makes it easier. So A, B, or C? So dissolve in water and hexane, boiling point less than 100 degrees Celsius, and melting point about 20 degrees Celsius. So this is going to be completely nonpolar, so it will not dissolve in water. This is also completely nonpolar, so it will not dissolve in water. This is an alkane, right? Alkane is nonpolar. And this is aromatic. It's also nonpolar. So it will not dissolve in water, so therefore by a process of elimination you get B.
And what do you even, like, why do you even give us boiling point?
Oh, because it's the same property. The melting point in terms of this molecule is fairly tiny. The boiling point is a bit less than 100 degrees Celsius. So you know that it's going to be about a dipole moment. It's not going to be ionic, and its interaction is going to be roughly a bit less than water. So the functional group is going to be, it's not going to have a lot of carboxylic acid groups or amide group. So alcohol. The melting point is about 20 degrees Celsius. It also tells you that it's also have a non-polar characteristics. So in this case, there's a polar head here, and this alkane group is fairly big and bulky, and it's also non-polar. So something along that line. That is probably a bit harder because you have to incorporate every single one of them, but just reverse the process and reverse the questions. So yeah. Trying to figure out what to do next with this one. Yeah, why not? So let's plow through the organic portion. I'm just going to go through it really quickly instead of like too details. We just have less than 40 minutes to go, so I kind of wanted to go. It's mostly going to be... Am I going to ask this at all? I don't think I'm going to ask this, but I do want to get it in terms of just a regular understanding of how things go. My point is that you have protein and DNA and inside your body, and basically everything else, the only thing that DNA does is just store, and everything else is done by protein in terms of your biological system. And the building block of the protein is basically these amino acids. And like I said before, the polarity of the amino acid is going to be important because it's going to dictate how they interact with one another and whether they're going to be in the inside of the particular enzymes or protein, or they're going to be on the outside, whether they're going to kink, whether they're going to make particular structures and so on. But before we go into there, what I want you to notice is that this is a stereocenter. That's a stereocenter, 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 stereocenter. That one's actually a stereocenter, but I don't care about that. Stereocenter, stereocenter, stereocenters, stereocenter, stereocenter, stereocenter. And I think I'm stereocenter, 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 stereocenter. And the only one that's not is I think that one. Oh, actually histidine is not. I think I'm just kind of being lazy about it. There's two amino acids that doesn't have a stereocenter, but the rest does have it. And I'm trying to figure out what it is. I'm missing one, but I'm just going to ignore it for now. So this is not a stereocenter. The reason why your amino acids are all stereocenters is because your DNA is also chiral. That is, you have alpha helix because each of the DNA molecules are chiral molecules. You have two of each kind of DNA. And the one that we have are just one particular type, one particular chirality. That's why everything spins in alpha helices instead of beta helices. And because it spins one way, the protein that it makes also spins in a particular direction. So they're all chiral molecules as well, except for a few. And the reason why there's stereohydrins, oh sorry, not stereohydrins, the stereochemistry is important, and why certain molecule in terms of chirality interact with your body but not the other one is because the same thing too. The building block, which is our DNA, is chiral. So everything else that comes with it have a chirality that propagates essentially to everything that we that makes up the body as well. So that's one. The other thing is that these amino acids are polar and non-polar, and for one side is going to be in the inside the degree of polarity is going to dictate how they fold. So if these amino acids fold with one another pointing inward, that means most likely they're either highly polar and you have ionic interactions, or they're highly nonpolar and they just basically hides away from the water. It depends a lot, but it could happen in both cases. Right. So these are your amino acids, and you have a bunch of them. Do you guys in your study, have you yet have to memorize these things or not yet? Some of you already have to, so that's probably good. I'm going to skip about, oh, right. Some of these are called alpha carbon in the amino acids. For those who already heard about the terminology, it's basically stereocenter. So it's kind of important. And the reason why I keep adding amide into one of your functional group is because when two or more amino acids combine together, they will produce water. So this will come out. So it's dehydration reaction, which we're skipping, and we're going to create a peptide bond. And all of these peptide bonds are basically amides. We're skipping the reaction name. The particular name of the reaction is dehydration. You basically get rid of the water here. And in the end, what you get is an amide. And all amides or all peptide bonds are amides. Hence, I keep asking about amides as part of your functional groups, because I do want you to recognize it as well. Oh, actually, it's condensation. Yeah, that's true. Sorry, it's not dehydration, it's condensation. I forget. Now that I'm skipping it, I'm not being careful with my word, but they're condensation reaction. I'm skipping that part. But more or less it looks something like this, right? So once your amino acid binds with one another, you get a linear chain that looks more or less like this. And what I want you to notice again is that some of them are polar, some of them are non-polar. This is kind of non-polar-ish. This is non-polar, polar, non-polar, and non-polar. And it will dictate in the end how they will fold. And some of these molecules also have a little bit of characteristic. That is, if you look at this one here, this one is a bit looking kind of weird because you can see that it's kind of scrunched up like that. So what happens is that these molecules are going to give you some kinks. Right, so what happens is that if you have this particular one, which I think is, do you guys remember what the functional group of this one is? For those who have to memorize the amino acids, I don't remember. I just know they kink because the structure of proline, there you go. So if you have proline inside your amino acids, that's usually where the amino acid would kink. That is, I have a linear chain of amino acid, and then once I have a proline, when I have a proline, you can see that it looks like a pentagon here. That's because there's a nitrogen here, there's a carbon there, and the proline is causing it to kink. So it's going to start moving this way. It's all about structures, and some amino acids, among others, have more characteristic than others. And histidines and prolines, I think, is the one that making things kinks. And proline here specifically is just you can see it that it's not the functional groups are not dangling out of the backbone of the protein, but rather it's actually scrunched up and it's forcing itself to kink. There's an angle here that's forcing it to kink. So there's among other things that you get. You can actually figure out the protein structure for a bunch of things if you just kind of Google online, and especially if you know where to go, such as this one, you can actually look at the primary sequence of proteins and so on. And majority of the time, the proteins are written in these one alphabetical symbol, just because it beats writing these out or drawing them manually, because they're They're long and they're kind of annoying to draw. So what happens is that people have a full name for it, and then they got lazy and they give it a 3-name syllabus, and they get even more lazy and just give it a 1-name syllabus. The same reason that we have skeletal structure is the same reason that proteins are written in one alphabetical symbol, and you have to memorize all of these because people are lazy. And sometimes you just have to just truncate everything. And again, it comes out to the fact that in the old days, you have to type these things. You have to type these things in a typewriter, and you don't want to type too many things, especially if you have like 100 different things to type. So if you just put A, B, C, M, L, R, L, L, P, and so on, there's so much less mistakes and so on. There's a lot of historical things where some naming structure arises and so on. Sorry, I'm just kind of jumping through it. You don't need to know it's about the biological system, but I do want to look at it in terms of just every single one of them just on structural view rather than individual interaction. Just looking at everything all in one go rather than looking at it. I just want to look at the big picture for now. And you'll fill it in the blank later on as you go to advanced classes. Your proteins, of course, is just a single line of amino acids that are connected one together. And there's different levels of structures, which the primary structure is basically that A, B, C, D protein name. And then you can start to make a secondary structure where molecule of the same proteins are starting to fold in a certain fashion. Among other things that you can get is a beta sheet or alpha helices, where they have hydrogen bonded molecules between one amino acid to the next. That's a secondary structure, so interaction between the same primary structure to make a secondary structure. The tertiary structure is basically you have multiple secondary structure that kind of clumps up together, and the last one is you have a quaternary structure where you have 2 or more chains of polymers that kind of coagulate together. Now, what I want you to notice about these whole thing is that they kind of have to form and they kind of have to fold properly in order to function, because it's all just site specific. It's all about the geometry. So if you have misfolding, that is something went wrong, one of the amino acids that's important, so you get rid of one of the proline instead of kink, you kind of makes a linear one, then you have misfolding, in which case the protein stops to function or its functionality decreased by quite a lot. So any tiny mistakes usually can, or any mistake could cause a misfolding, but majority of the time we're kind of buffered around it, because even though some of the proteins are different, you have a lot of different proteins, majority of them kind of behaves as a group, that is, as long as the group interaction. Once you start replacing a lot of them, that's when you start making a difference. But if you just have 1 or 2, especially in, say, not so important places, like right here, so as long as this particular molecule on the surface is polar, usually a tiny bit of interactions and replacement between one protein with another is not going to make that big of a difference in terms of its overall structures and functionality. But the one important one is that you can have misfolding and so on. So how many DNA is needed to decode a particular amino acid for those who are taking the class? 3. So you need about 3 of your DNA, which is codon, and it will get into a single kinds of amino acid. And how many different kinds of DNA are there? 4. Right? So you have different kinds of, you have 4 different kinds of DNA molecules, and essentially, if you have 3 possibility on each one, so I have 3 times 3 times 3, so you have actually quite a bit of combinations. And if you, hold on. Oh, sorry. Each codon is 3 DNA molecule, and each of DNA molecule could be a combination, so either 4. So 4 times 4 times 4 is 16 times 4 is 64, right? So if you notice that the possibility of the codon is 64, but you only have 20 different kinds of amino acids, that's also kind of a different way that our body it allows some DNA mutation that doesn't change your protein by that much, because we have 20 amino acids and then we have 64 different kinds of combinations. So you can have you can have a lot of different kinds of combinations, and one of these could be replaced by something else, but you'd still encode for the same type of amino acid. So there's some buffer in terms of how our DNA changes. Even though each one of us, our DNA is slightly different, we are more or less, the proteins are more or less identical, just because tiny mutations sometimes, or majority of the time, will still decode the same amino acids. What's more important is that if you have erasure, or I forgot what the terminology now, if you have DNA damage that you subtract 1, do you guys remember what it's called? It's because, sorry? No, that's not it. There's a specific one that you just basically splice up one, so you can get rid of an entire codon. So that's, huh? Frame shift is something of what it is, but I don't think that's exactly what I was looking for, but that sounds close enough. The problem is that one of the bigger problems is that if you just get rid of one instead of replacing one DNA with another, then all of these are shifted. So once everything is shifted, that's when everything got all screwy, because your letters are no longer legible, because deletion, there you go. Man, that's so simple. It's deletion. It's deletion. When you have a deletion, your codon shifts. Now the code is completely different, because now instead of measuring UUU, because of deletion, it's going to measure GUU, UGG. Then that's kind of a bigger DNA damage than the majority of the things that you have, because deletion will really shift the translation of the protein. That's usually the bigger problem. So that's one. And of course, if you have DNA damage, and there's different kinds. So essentially, if you have your DNA is sufficiently changed, then you get your proteins, whatever it is going to be slightly different, or widely different than it's supposed to be. Then you start getting sick. So you can have a mutant that doesn't allow chlorine ion to go in, then you get cystic fibrosis, or which cause your DNA to be filled in with liquids. So that's just kind of the general gist of it. It's all about structure. If your structure is not right, you're not going to get the right functions. And if it doesn't have the right function, the building blocks doesn't stick together as well, then your Jenga will fall apart and you get sick. That's all I want to say, really. It's just that level. It's all about structure, especially once you get to biochemistry. Hence, you have to memorize every single one of them, because every single one of the protein structures and so on is important. No, later on. Yeah, you have to memorize, I forgot what it's called, but you have like this thing, like the something triangle, I forgot the name for it. There's like some kind of step in your glucose oxidation, so lactose something. You have to memorize the locations of whatever functional groups of the amino acid is supposed to be. And it makes this particular cove of reactivity. Something along that line. Sometimes you have to memorize those as well. And the important part is that if you have damage on these specifically important functional sites, then that's where, even though you have only one mutation, the mutation is quite substantial. So something like that. So if something in position 40 is replaced by something else that are entirely different, then it stops functioning altogether. So there's a lot of buffer, but some areas are more important than others. So that's the effect is going to be larger. Okay, so that's mostly what I want to say. We have exam next week. Let me see if I can post something online as practice. We'll do the same thing as last time. We're not going to do a 4-hour exam because that's just an overkill. I'll give you guys a buffer of an hour, right? So we'll just start the exam at 11, so that people who lives further away don't have to kind of shoot. I forgot. I need to be here like 10 minutes ago, but that way you have. I'll keep the exam for 2 hours instead of 3 because 3 is too long. 2 is enough. Yeah.
In case that don't get to when you have an example, can we at least get a list of the topics that are going to be on there? Because I know we like canceled out.
That's a really good idea. So can you have your class planner and kind of go to the thing on the page where topic? I'm trying to figure out where it is.
All three of them?
Yeah, for part 3. So assume whatever it is that you're tested in part 1 and 2 is going to be tested again. But we are truncating quite a bit. Like we don't do chemical reactions, so I want to make sure that's kind of eliminated from our list. So this is what you have on the list. I'm just going to go from the bottom. You don't have to do number 12 because that's enzyme. 4-level protein structure, you don't need to know. Function of enzymes, you don't need to know. You do need to know micelles and lipid bilayers, stereoisomers. You don't need to do number 7. And then basically that's it. So the rest you should be able to do because that's kind of the large portion that we did. So we are going to do 1, 2, 1, 2, 3, 4, 5, 6, 8, and 9. And right, so that's what we did. So that's what you're going to see. All right, see you guys next week. Next week is going to be the final. I'll upload something. I should have something that I can upload really quickly. And we'll go from there.